It is by small and simple things that great things are brought to pass. Atoms form the basis of all matter, and the behavior of their primary constituents can be used to describe a wide variety of phenomena. We will start with a summary of quantum electrodynamics, in which there are essentially three things to consider, mainly protons, electrons, and photons. These fundamental entities are neither particles nor waves, but rather exhibit properties of each. Their existential characteristics can be modeled by Schrödinger's wave equation. These wave packets do not have definite properties until they are measured, like a rainbow, which does not exist unless it is being observed. An observer will, however, have different probabilities of seeing a rainbow or a subatomic particle based on the current conditions, but the exact properties of either cannot be predicted with arbitrary precision. According to Heisenberg's uncertainty principle, the accuracy of positional knowledge and that of momentum are inversely related. Physicists are thus forced to represent characteristics and events as amplitudes, which relate to probabilities, in that a probability is the spatial integral of the absolute square of the amplitude over the region. Amplitudes are tensors with directions which correspond to the quantum state of the system, and can thus account for phenomena such as interference. The amplitude of a simple event is the sum of the amplitudes of all the possible manners in which the event could have occurred, and the amplitude of a complex event is the sum of all sub-events that comprise it. Calculating these amplitudes is complex due to the immense number of ways in which a result may arise. The seemingly simple becomes complicated when infinite numbers of paths and interactions are considered. For example, a photon and electron moving through space could go directly to their destinations, or the photon could degrade into an electron and a positron, which would annihilate with the original electron to form a photon, and there are infinitely many other ways that this event could occur. Note in this case that a positron is a virtual particle and merely an electron traveling backwards through time, and also that scenarios with more virtual particles are less likely because the amplitude is multiplied by the fine structure constant raised to the number of couplings. We will now discuss quantum chromodynamics, keeping in mind that diagrams and amplitude calculations can be made in nearly the same manner as was done in electrodynamics, except now we will be considering the behavior of quarks, which are the components of hadrons, baryons, and mesons. These quarks have charges, and whereas in electrodynamics there are only one type of charge to consider, now there are three, and these charges are named red, green, and blue. Quarks interact through the strong nuclear force, and the mediating gauge bosons of this force are gluons, of which there are 8 types, since they are the generators of the special unitary group which coincides with the 3 color charges. This color charge is conserved, and quarks can change colors by releasing and absorbing gluons. One major difference from electrodynamics is that gluons can couple with one another, whereas photons cannot. Chromodynamics is a difficult field due to the self-interacting nature of gluons, the fact that quarks experience confinement, and also because renormalization is not nearly as effective. Overall, electrodynamics and chromodynamics basically consist of the summing of amplitudes over all conceivable paths and interactive possibilities, and the obtained probabilities form a basis for all electromagnetic and strong interactions, and thus are capable of describing all phenomena if they can be perfected and united with the weakened gravitational forces.